Good morning, everybody. Well, let's see. Oh, thank you. Corey, Brandon, Rochelle, Matthew, thank you. Uh, Ronald, thanks. Oh, first, here is an announcement that might help you. I don't know if I already talked about it or not, but if you go to my website and you have the address of my website. Here it is. So, yeah, if you go to my website and click on teaching, right here, teaching. Click on teaching, you will have your courses and the other courses, all right. Let's see, how can I get rid of, okay. Oh, this is your course, 432. If you click on this one, you will have this spreadsheet. And that's the same spreadsheet I gave you at the beginning of at the first day of class. Now, the difference between this spreadsheet and that one is that if you click, oh, here is the test number 1, that is of course gone. But if you click on test number 1, you will have a bunch of uh, problems, review problems for test number 1. Okay, so review problems for test number 1, uh, which will help you. It has also integration and those type of stuff. It goes even beyond test number 1. Now, going back, if you click on test number 2, which is again, we are done with it, you will have again a bunch of review problems, all right? Here, review problems for test number 2, which starts from sequences, series, and then power series, and right here, bunch of power series. You want to find the radius of convergency, and not only integration, but practice on, for example, Laurent series, this one number 22 or number 21. They're asking about Laurent series, all right? So the same thing, by the way, I'm going to go back to the spreadsheet. The same thing for test number 3, which is right here. If you click on it, again, you are going to have a bunch of review problems, right? So these review problems, okay, here comes the finding residues, all right? Finding the residue, and then applying a residue theorem in calculating these integrals, which basically is topic of, sorry, it was topic of Tuesday, and I will continue on this one today. And a bunch of other problems. Okay, so these problems will be very helpful, and I will definitely recommend that you form study groups and do these problems together and try to learn from each other, right? All right, let me get rid of this. So it is on my website, remember. Okay. Now, well, after this one, I remember last time when I said, if you have a question, let me know. And one of you had questioned about Laurent series and the advantages or um, the benefits of knowing Laurent series. I'm going to go very quickly because, after all, uh, my understanding is that you studied Taylor series and Laurent series, and even you practice on it. But unfortunately, some of you didn't do very well in your uh, test number 2. And I think this quick review will be very beneficial, right? So, to everybody. And if you already know how to do it, again, yeah, it doesn't hurt to listen to this review one more time, okay? All right. So everything started with Taylor series. Now, what is the difference between Taylor series and Laurent series? Well, when you do Taylor series, the function is a beautiful function. It's analytic at that point that you want to write its Taylor series. Okay? So it is not a singularity, it's not a bad point, it's a good point, and the function is analytic at that point. If that is the case, we can have a series representation of f of z with the power series centered at alpha, centered at that point. Okay. Sometimes that point is 0, so we call it Maclaurin series, but that's now the point is theoretically, when we go through the Taylor series theorem and its proof, this an is actually the nth derivative of the function at alpha divided in factorial. We can even express this in terms of an integration. So it is integral over this closed curve, okay? This closed curve. And in denominator, you have s is the variable of integration, s minus alpha to the n plus 1. So that gives you Taylor series. But the fact is, when you write Taylor series and later Laurent series, these series are unique. And a lot of time, we use shortcut. That's easier. That's easier to write the Taylor series or Laurent series. And for doing the shortcut, we use the Taylor series of important functions. Oh, these are those important functions, starting with the exponential function. Right? Always. E to the z is right here. And this is true for all values of z. There is no restriction. We have cosine of z. All right? Then we have sine of z. And another important one that for these three, we don't have any restriction. Those are valid for all values of Z. But we have another one called geometric series. For this one, we need modulus of Z to be less than 1. All right. This is the geometric series. And you had a couple of uh, numeric geometric series also in your test number 2 that you wanted to make sure it converges or not. And a lot of you did very well on that. As soon as modulus of Z is less than 1, it converges. Bigger than or equal 1, oh, it could. It diverges. So, okay. And since this power series representation of functions are unique, we will use the shortcuts, all right, for these. So for Taylor series, the function is analytic at that point. It's not a bad point. But when it comes to Laurent series, that point is a bad point. Okay? Is a bad point of function. Can we have a power series representation for the function? Yes, we can. That is called Laurent series. But in that series for Taylor series, it starts from 0, n equals 0. But here we have also negative numbers, negative powers of Z minus alpha, all right? Which means Z minus alpha can also be in the denominator in that expansion. That is Laurent series. Now, a couple of things are extremely important here. And that is why we like Laurent series. First of all, this is the AN. When n is 0, 1, and so forth, we are going to have positive exponents of Z minus alpha or a constant. But when n is negative, for example, -1, right away you see a -1 is 1/2 pi I integral over that closed curve. N is -1, all right? So denominator will be S minus alpha to the 0, which is 1. So it is f of s ds or f of z dz. As you know, the variable of integration is a dummy variable over that closed curve. Well, in integration theory, we always would like to find this integral of f of z dz. Okay, so the first advantage of writing Laurent series is this one, that will give you the integral of f of z dz is 2 pi I a minus 1. What is a minus 1? A minus 1 in this expansion is here when n is -1. A minus 1 times z minus alpha to -1. So this a minus 1 is the coefficient of this in that expansion. Okay, That is the most important part of Laurent series, because the number multiplied by this, which we call it residue, by the way, right, is multiplied by 2 pi I, will give us the value of integral, all right? Value. That is the most important part of the Laurent series. All right. I gave you earlier some examples. I'm not going to repeat those examples, but as I said, when you write the Laurent series, you are going to have this. Let me see. Let me see what happened here. Goodness. Okay, so here's an example that we want to write the Laurent series in powers of z, which is valid in this area, all right? And when you write that Laurent series, you get this. So, which means all negative powers. Anyways, the second important part of Laurent series is after writing this Laurent series, you put all the negative exponents of the function on one side, positive exponents of z minus alpha, another part. This is called analytic part of the function. This is called the essential part of the function, right? Putting all the negative exponent of z minus alpha together. Now, the second part of the second part of the Laurent series, which is important, or second advantage, I would say, is that what did I do with my R? Oh, Dale Dodson, I will come to your question in a moment. By looking at the essential part of the Laurent series, we can decide whether that particular bad point is a pole of order n or removable, or it is an essential isolated or non-isolated singularity. What kind of singularity is it? Okay, so the second advantage of Laurent series is to determine the what kind of singularity we have, all right, to determine the kind of singularity. So basically the isolated singularity, we don't talk about non-isolated. Is it an essential singularity, removable, or pole, right? So is it a pole? If it is a pole of order n, and when n is 1, it will be a simple pole, or is it a removable singularity? or is it an essential singularity, which means we have infinitely many powers of uh, z minus alpha. So two main advantages. And as soon as we notice what kind of pole it is, we can then go ahead and find residue and so forth. All right. Now, the question is, I see Del Dodson says, how do we know where the Laurent series is valid? Well, a lot of time, that question that you're asking comes when we are dealing with, let's say, a fraction. Okay, we are dealing with a fraction. And as soon as you are dealing with a fraction, I'm trying to get an example here. Let's see. But yeah, why not? Let's look at this example right here. So it says find the Laurent series that is valid here. Well, valid in this washer here. This is z minus 2 modulus equal to is this circle, equal 1 is this circle, but we want the modulus of z minus 2 be between these two. So we want this, okay? And most of the time, of course, you are going to use, when you're dealing with functions like this, you are going to use geometric series, all right? This is going to answer your question, Del Dodson. We want to use geometric series. And it says in powers of z minus 2. Well, see, none of these, if I want to apply geometric series, none of these are powers of z minus 2. So I better do partial fraction, separate them. Here is the first step. Now you want to write each one of these in powers of z minus 2, okay? In powers of z minus 2. Oh, of course, it's got to be valid in here, right? Oh. Let's just start with the first one, this one. Since you want to write in powers of z minus 2, you better make z minus 2 appear somehow. And in this case, it's not that bad. You just add 2 and subtract 2. Oh, you got z minus 2 right here. And it seems that it is ready for geometric series. However, okay, be careful now. However, geometric series looks like this. Here is geometric series that we use. This is geometric series. Zero to infinity. And the modulus of W has got to be less than 1. So if I want to use this one, by the way, this one has a sort of a counterpart when you replace W by minus W, you will get this one. So, you got to know these two by heart. So this one, I replace W by negative W, so I will have negative 1 to the n, WN. So in those fractions, most of the time we will use one of these. And in order to use one of these, of course, we need modulus of W be less than 1. Okay? All right. So here is this one. I made this one appear, but we got to have 1 plus W or 1 minus W. Let's factor 2. If I factor 2, I'll have this one. Do I need modulus of this to be less than 1? Oh, look, if modulus of this is less than 1, z minus 2 will be less than 2. Yeah, that's what I want. Less than 2. Oh, be careful. If we wanted the Laurent series in this area, we would do it differently. Okay? So now I can use that geometric series on this one because I know that in that washer, modulus of this guy is less than 1. So here is the first one. Now comes the second part, comes this part, all right? I took care of this. Now this one. Well, for that one, again, you want in powers of z minus 2, better make z minus 2 appear, right? I just added and subtract. Now, in that washer, modulus of z minus 2 is less than 1. So right away, we cannot. See, modulus of z minus 2 is bigger than 1. But we want 1 plus W be less than 1, right? So you factor this one. If you factor, you will get 1 over 1 plus this. And now modulus of this is less than 1. You can apply. Think about this as W and apply that geometric series. Here we go. So you can also take z minus 2 inside, multiply. So the series or the Laurent series of the function in powers of z minus 2 will be this and plus this. These are all sort of positive and constant, positive exponent of z. This is the negative powers of z, all right? And remember, the coefficient of 1 over z minus 2 will give us the residue. So the area that they give you, Del Dodson, is the key. So what I did, I wrote the Laurent series of this function for this washer. Can I write Laurent series of this function outside this big circle? Yes, we can, right? Outside that circle. But always you got to be careful that you are using one of these two. And the condition of using one of these two is that this W, modulus of W, has to be less than 1. These are the key, okay? And that will tell you whether here directly use z minus 2. In this case, it was less than 1. I could. Or in this case, I could not. I had to have reciprocal of this to make sure that modulus of this guy is less than 1, and then use geometric series. Okay, I hope somehow I answered your question. This became n plus 1 because we had a factor of 1 over z minus 2 outside. I took it inside. So z minus 2 multiplied by this gave us z minus 2 to the n plus 1. All right? Very good. Okay, now, so let's see. Yeah, last time, as part of applications of residue theorem, and I told you in calculus we have a bunch of integrations that we don't know exactly the value of integral, but we can convert it. It is an integral from calculus 2, but we can convert this into an integration in complex analysis in this course and find the exact value of this thing. Okay, so I gave you an example and I assigned a bunch of problems from your book, which were here, problem 1 through 9. I hope you worked on those problems. See, in mathematics or any subject, by just listening and watching, you can't perform. If you go to a concert and somebody is playing violin, by watching that individual, you don't learn to play violin. In order to play violin, you have to put a lot of time, practice, and practice. Same is true in mathematics and any topics that you want to learn. By watching me to do this, actually, I am sort of giving you that concert because I know I am a good teacher, by the way. So I make it easy for you to follow me. You can follow easily, but that doesn't mean you learned it. No, you didn't. You just followed my explanations. In order to learn it and do well in your test, you need to practice. You need to do these problems, okay? All right. Now, today I am going to continue this topic. Well, let me take care of the lecture, and then if you have time, I will look at that number 3 or 6 of 16.4 and tell you how to do it, okay? But first I need to cover, we don't want to fall behind. Sorry. Or, sure. Um, and if all right. Okay, now today I want to talk about sort of uh, another type of integration that you had in calculus 2, but you couldn't find the exact value. Now, before doing that, do you remember in calculus 2, we had a topic called improper integrals. Improper integrals, what are those? Oh, there are several types of improper integrals. One of them, see, when we integrate, always we like to do the integral from a to b. These are numbers, and f of x dx. I'm talking about calculus 2, okay? Where this function f is defined very nicely, is behaving on that interval. Usually it's continuous, all right? It's continuous. Now, so a and b are numbers. What if one of them becomes infinity? Oh my goodness, all right? That is called improper integral. What if this guy becomes negative infinity? That is called improper integral. What if the function is not continuous, had a bad point, had a point of discontinuity in that interval, right? So that is again called improper integral. It's funny, okay. All right. Now, I am going to talk about or concentrate on the in, uh, improper integrals that they look like this. For example, 0 to infinity. When you have such a thing, how do you justify this? Well, 0 to infinity, the function is defined. Uh, you have something like this. Let's say you have a function f of x like this, going like this. Well, oh, maybe why not? Let's since I don't want this to be okay. I don't want to be asymptotic with y-axis. So how do we treat this type of integral? Well, what you do, you integrate from here 0 to this number. And remember, integral from here to here gives you this area. So the interpretation is this. You integrate from 0 to b, f of x dx. After integrating, this is the number now. It definitely depends on b. After you take care of this, then you take limit as b approaches infinity. Okay, so that is the way we interpret this type of improper integrals. Same thing with negative infinity, all right? Same thing with negative infinity. When you are dealing with integral, let's say from negative infinity to 0, let's say, I'm not going to go with f of x dx or a function, g of x dx, doesn't matter. Yeah, let's say g of x dx. I don't want to have the same function. How do we interpret this one? Well, so you have a function that is defined from negative infinity to okay, I better have one at a time. Okay. All right. So the way it works is this, that you have a function here's y-axis, x-axis. Let's say the function is working like this one. This is g. So in this case, what you do is you integrate from this number here, let's call it a y naught, to 0. You will get this area. And after getting that area, so you integrate from a to 0, gx dx, and then you let a approach negative infinity, and that's limit, right? You take limit as a approaches negative infinity. So that is how we treat this type of improper integrals. Now, sometimes this function that we are working with is an even function. What do we mean by an even function? Okay, let me give you the definition of even function. So f is an even function if f of x and f of negative x be the same. So f of x and f of negative x be the same, right? A good example of an even function is cosine x. For example, y equal cosine x is an even function. Geometrically, when you have f of x and f of negative x are the same, geometrically means the function is symmetric with respect to y-axis. So in general, even functions graph-wise, right, graph-wise, the picture of even function is symmetric. With respect to y-axis, with respect to y-axis. And I mean, the good example, of course, is cosine, or I will give you more examples. Here is y equal x squared. Y equal x squared is symmetric with respect to y-axis, all right? It's symmetric with respect to one side is the mirror image of the other side. Or in general, why not? Whenever the the exponent is even, it will be. And the same thing I said is true for when it comes to geometric picture, is true for cosine x. Here's cosine x, which goes like this. Right? This is y equal cosine x. These are examples of even functions. Here is y equal x squared cosine x minus x sine x is even. Why it is even? Well, instead of y, let me okay, put functional notation. Because if you replace x by negative x, f of negative x is, okay, negative x squared cosine of negative x. Then comes this part, replace x by negative x, sine of negative x. Remember, cosine of negative x is the same as cosine x, and x squared in here. So this will be x squared cosine of x. Negative negative gives you plus, but sine of negative x is negative sine x. See, we got back to the function itself, right? So I replaced x by negative x. I just noticed that, oh, well, look, this is f of x. That is how we prove that the function is even. You replace x by negative x and show that, all right, they are the same. What is the advantage of knowing a function is even in our discussion today? Well, when a function is even, here is the advantage. When f of x is even, then the integral from negative infinity to 0 of f of x dx is the same as integral from 0 to infinity f of x dx. You just do a change of variable in this one. A change of variable. Replace x by negative t, right? This becomes, maybe I should do it because I know that a lot of you are pretty weak in your calculus material, because here's proof. In this one, make a change of variable. Negative t. Then negative infinity to 0 f of x dx becomes, now when x is negative infinity, t becomes infinity, right? So infinity to 0 f of negative x t, I am replacing x by negative t, and dx becomes negative dt. But since the function is even, f of negative t is the same as f of t. And this negative, you take it out, and it will become, oh, I'm going to do it, make sure all the steps are taken care of. So that is negative coming out. And f is even. Okay? But when you switch the limits of integration, the effect will be what? Negative. So this is 0 to infinity of f of t dt, okay? But t is a dummy variable. You can say f of x dx. So that's what I claimed, and this was a little justification for it. Now, what all of this has to do with complex analysis? Complex analysis. Oh, wow. Okay, here is an example. In I would like to do this problem. Let's say 0. Well, I could say negative infinity to infinity, but well, let's say 0 to infinity. Dx 1 plus x to the 4. Well, when it comes to calculus 2, of course, this is an improper integral. An improper integral, we have several tests to say it converges or not. And this one converges because we have x to the 4, right? It converges. But what is its value? We don't know. When you are in calculus 2, You don't know what is its value. You simply can say, oh yeah, I know this is uh, this converges. But right now, because the integrand that I'm doing, the function is even, so I can say this is 1/2 of negative infinity to infinity, because zero, negative infinity to zero is the same as this one. Keep that in mind. Next thing I do, I will look at the function in complex f of z, which is 1 over 1 plus z to the 4. Yeah, I could have, and this is a simple one I'm doing for you. And in complex, we always integrate over a curve, all right? So we need to create a sort of contour, a curve, and integrate this thing. So the contour or the curve that I'm going to consider in this case would be this one. This is a semicircle. So let's say it says, sorry, or I need to do this to make sure that, all right, I have a decent semicircle. This is x-axis, and here we go, y-axis. So let's say the radius of this semicircle is r. So here is r. Here is negative r. By Cauchy theorem, if I integrate counterclockwise, going in this direction, from negative r to r, then on this one, let's call this one CR. So consider the f of z. Out of this, I will create f of z. And integrate this over this closed curve. And when you integrate over this closed curve, you're going to have apply residue theorem, all right? So consider this one and use residue theorem to compute the integral over this closed curve. To compute but the integral over this contour, this closed curve, is from negative r to r, then on this semicircle. So here I'm going to write in two pieces. So one is from negative r to r, f of z dz, plus the other one, cr, f of z dz is going to be on the right-hand side using residue theorem. It will be 2 pi I residue at the bad points of the function in this that are inside this contour, inside this, all right? So 2 pi R sum of residues. I'm just saying sum of residues, all right? ZKs. And these are gotta be inside. But now we need to find the bad points of this function in here. Oh, the bad points are, of course, zeros of the denominator. So singularities, all of them are simple poles. So 1 plus z to the 4, 0 will give you z -1, which is e to the pi I, plus 2 pi I, 2k pi I, right? Finding the roots. So we have four of them, of course, but the ones that are inside, one of them is z1, which is e to the pi over 4 I. The other one z2, which is e to the, when k is 1, 3 pi over 4 I, okay? And two more. But the other two are outside. So I'm talking about this one, z1, and this one, z2. So it will be residue, 2 pi I residue as z1 plus. Now, let's analyze this equation. When you are on from negative r to r, the parameterization, it is just x-axis, no y involved. So on the negative r to r of x-axis, z is just x plus y is 0. So the first integral, this one, becomes negative r to r f of x dx. And f of x dx is that dx 1 plus x to the 4. Then we have on this circle, right? On that circle, modulus of z when you are in this, modulus of z is r. I am going to use ML inequality later. So it will be just let's write it down for the time being, f of z dz. On the right-hand side, though, here, it will be 2 pi I residue at z1 plus residue at Z2. How we will compute this one? Oh, this, no big deal. Well, actually, both are simple poles, so it will be. I can give you that residue at Z1 is um, 1 over 4 square root of 2 and minus 1 over 4 square root of 2I. And residue at Z2 is 4 square root of 2 minus 4 square. So some of these two, this one cancels with that one in here. So we know what we have on the right-hand side. So the equation summarizing this, we were analyzing this, right? We were analyzing. So that equation becomes, I'm going to rewrite that. So it becomes negative R to R dx 1 plus x to the 4 okay. I'm just rewriting this equation plus this one f of z dz is 2 pi I sum of those two residues, some of these two residues, all right? So this cancels, so you will have twice of this. So it will be negative I divided by 2 square root of 2. So I and I will give us another negative. So this is basically pi over square root of 2. Very good. Now, remember, we were integrating here in this one. Now I am going to let, but we are after this. Now we are going to let R approach infinity. When R approaches infinity, sorry, see what happens. As R approaches infinity, if I can prove that this is going to be 0, then, okay, let me write it down. If we can prove that limit as R approaches infinity of this integral, CR, f of z dz, is 0, then what happens? This will be 0. Here, we get the integral from negative infinity infinity dx over 1 plus x squared x to the 4 equals this one, because this is, we found the value. Okay, isn't that nice? Now, can we prove this one? Of course we can. Just as a matter of practicing, I am going to use ML inequality, all right? We use ML inequality. In this one. Because on that semicircle on CR, Z is R e to the I theta. Theta being between 0 and pi. Or definitely modulus of Z is R. So using ML inequality, the length of the curve is a semicircle. So CR f of Z dz is less than or equal to M will be 1 over R to the 4 minus 1. L will be pi R. So as R approaches infinity, this goes to 0, this goes to 0, done, okay? Which goes to 0 as R approaches infinity. We are done. So, but this is from negative infinity to infinity. The answer to the main problem that I started from 0 to infinity, dx over 1 plus x to the 4 is half of it, all right? Here is from negative infinity to infinity is this one. So it's half of that, and that is pi over 2 square root. Beautiful. We found the value. Okay, we found the value. So in finding the value, I went through all the details that needed, but I have a very good news for you.